Hello, welcome to session number 28 in the series Microwave and Millimeter Wave Circuit Design. My name is Anurag Nigam, and in this session we are going to talk about exact class E analysis, exact class E design for any Q and any switch on duty cycle. Now this paper, most of the work in this session is from this paper by this title, exact analysis of class E tuned power amplifier at any Q and switch duty cycle. So this is a switch on duty cycle, right? And this is from IEEE Transactions on Circuits and System, February 1987. And this is the most comprehensive or a complete treatment of a class E, right? And we will discuss about how this is done, and then I will implement it as a numerical solution for this, right? In this paper they are using 2D Newton-Raphson method to solve the equations for class E, and then from that they are designing a class E. I'm going to use another technique which is called a graphical technique to design a class E amplifier, right? So now let's get started. Now consider two figures, figure 96 and 97. In this figure 96 you see that the switch is off, so when switch is on. So when the switch is on, CSH is not in the picture. CSH is shorted out. So when CSH is shorted out, so this is for a duration of theta between 0 to 2 pi d, where d is the switch on duty cycle, right? So in this period the CSH is basically shorted out. Now in figure 97 the switch is off. So in this case CSH is part of the circuit. So if I consider a Kirchhoff loop for in figure 96 and 97 for the output network, then I can see that there are going to be two frequencies. The figure 96 where switch is on, the resonant frequency is going to be so let's say it's going to be A1, right? Or A2 rather, right? So let's say A2. So let me show F2, resonant frequency of load generator F2 is higher, so that means it's on, right? So let's look at what that is. So we are doing an exact class E. So let me just put a title here, EXACT, exact class E design. Right? Okay. So in case of duration 0 2, so this is omega t theta 2 pi d. So this is going to be switch on. So for switch on, CSH is shorted out. So let's say the frequency is F2, isn't it? Let me just check. Okay, so yes, F2 is higher, right? Okay, switch on, frequency is F2, and the normalized frequency is A2, which is equal to F2 by F0, where F0 is the switching frequency. Now if you remember, the residual JX is because of the same reason, because CSH is being switched in and out. Is switching frequency. So now in this period the switch is on, so you basically your F2 would be equal to 1 over 2 pi root of LS and CS. So where you can see, this is LS and CS and this is CSH. Now for a duration which is between 2 pi d and 2 pi, the switch is off. So in this case the equivalent capacitance is going to be equal to CSH into CS divided by CS plus CSH plus CS. And then you have got a frequency which is much lower is going to be equal to 1 over 2 pi root of ls C equivalent, correct? And in this case, the relationship, so basically A1 is normalized frequency F1 by F0. So in this case, we have F2 is higher, and then you have F0, and then you have F1. Okay, so what we are going to do is, okay, as this paper goes about, so you can read this paper, you can find this paper online, and you can read this. So I will, let me just make sure I'm recording this. What happened? Oh, cancel. Okay, it is over here. Okay, so it is recording, so I was distracted. Okay, so now we can do this. Okay, what I'll do is I'll refer to its equations, okay, which are in the appendix, and which I will also write here, over here. Okay, so the way to solve this is, let's consider an on condition. So under an on condition, okay, under an on condition, okay, come on, okay, under on condition, the summation of voltages, okay, so if you refer to here, under on condition, VO, which is over here, VO plus VC, which is voltage across the series cap, and VL, voltage across the series inductor, summation of this is going to be 0, right? Because the switch shorts this node, right? So VD basically shorted by the switch, right? So then in that case, we can say that under on condition, let's say an on switch, just 1 second, bear with me. So under switch on condition, which is between 0 omega t and twice of pi t. Okay, at this point we have VC plus VL plus VO equal to 0, correct? And then we are going to have IC or ISW, I would say. Okay, so the current is flowing, so in this case the current is, all the current is flowing through the switch ISW, nothing is flowing through the capacitor CSH. So ICSH equal to 0, correct? So in this case ICSH is equal to 0, and ISW is going to be IDD or ID, or rather IDC you can say, minus IO, correct? So this is one equation, this is another equation, right? And then we can express these equations, right? So if you consider sinusoidal and then you express this equation, then you can have IO S in Laplace domain is SIO 0. So this is the initial condition at t equal to 0, minus VC 0 divided by L divided by S square plus twice of, let's say, okay, okay, so it will be omega A1, okay, divided by twice of Q1, or it will be R by twice of L plus omega naught 1 square. Okay, okay, so in this case, let me tell you what is omega naught 1. Equation number 1 says is omega naught 1, way up. Okay, omega naught 1 is 1 over root of LC. Okay, this is under the on condition. Okay, so this is CS. Okay, LS and CS. So omega naught 1 is your F1. Omega naught 1 is twice of, or rather F2, right? So omega naught 1, I would rather write omega naught 2. Omega naught 2 is going to be 2 pi of F2, right? Which would be, right, which will be 1 over root of LSCS. Correct? Okay, so this is the condition under switch on case. Okay, so this is one equation. The other equation is when the device is switches off. So in this switch off case, you have got the similar equations. So V D, which is the voltage across the device, is going to be V L plus Vc plus Vo. Correct? And in this case, ISW is going to be equal to 0, and ISH is going to be equal to ID minus IO. And then the initial conditions are at turn on, so that is at 2 pi D, right? So at this point, okay, where it turns on, that's the initial condition for this set of equation, or T1, right? So for that, I can write Laplace equation as V D is equal to, in terms of S, right? Vd in terms of S is equal to I0S times of R plus SL plus 1 over SC plus the initial conditions on the capacitor and the inductor, VCT1 by S, so that is for the capacitor, then L times of IO T1 e raised to minus st, e raised to minus st. Okay, so this is that condition, and this will result in, and another equation for the current is going to be equal to ICC or ID plus S square LC1 I0 T1 initial condition minus S times of C1 VD T1, that's the initial condition on the drain voltage, e raised to minus st divided by SLC1 S square plus twice of alpha S plus omega 1 square, where omega 1 basically will be equal to 2 pi f1. Okay, so I'm here the conventions kind of different here, right? So the way I have done is changed f1 f2, right? So don't worry about this. So f2 is for this figure of switch on case, and f1 is for the switch off case. So that's how I have done this. Okay, so now I have a1 and a2 are the two variables, and there are two equations, right? Okay, so if I was to do inverse Laplace on that and find out the two equations, okay, they would be over here as 31 and 32 here in this paper. Okay, so let me just bring up that. So that's that equation, equation number 31, and then there is another equation 32. So there are two unknowns, a1 and a2, and then there are two equations to solve it. So basically we have to solve this equation. Now this is a highly transitional equation, and if you do a 2D Newton-Raphson, you might not get the right answer. Depends on the initial guess, because it does some kind of undulation near the zero plane. So basically Newton-Raphson is based on slopes, and if there are two local minimas nearby, then you can be bouncing between the two local minimas. So this can Newton-Raphson method, which they use in this paper, which I implemented also, gets stuck on those local minimas, and always you do not get the result. Okay, so then I tried another technique which is called a graphical technique, in which I know, so let me show you another figure of A1 A2. Okay, so if you see the figure number A, okay, so for a duty cycle of 50%, A2 A1 basically is around 1. So 1 is basically fundamental frequency, right, f0, and A2 is going to be f2 by f0, and A1 is going to be f1 by f0. Okay, so these are going to become asymptotic as you increase Q, and they will come close to f0. Okay, but still there will be a residual Jx because of this reason, right? So this is versus Q, okay, for a given duty cycle. Now this algorithm doesn't place any restriction on duty cycle or any restriction on Q. Okay, so all you have to do is using these two equations, which you can write your own numerical method. I have written my own, you can write your own, and solve these two equations, equation number 31 and 32, which are over here. 31 and 32. If you can solve these two equations, you will be able to get the design. Okay, so the way I do it is I have coded it in a Matlab. Okay, so what I'm going to do is I'm going to put you on a pause, and I'm going to, so there is a Matlab program which I have written. Okay, so this is in two parts. One is saying refining class E. So basically it will compute A1 A2 upper lower limit. So basically what you do is you know that the solution is in certain region, okay, of A1 A2. So you decide the lower limit and upper limit of A1 A2, and then discretize the space in between, find out the solution in that region, and then you take the solution and then put again lower and upper bound on A1 and A2 and expand this and subsample it to a higher or rather to a lower sample time, right? So basically you sample it much more, refine the sample, so that way if you keep doing it for a number of times, you will get a very good result at the end of this, right? So let me just, okay, why is it stuck here? So this basically is a code which I have written, which is doing that only. Okay, it is refining, A1 A2 till you converge to a solution. Okay, so once you converge to a solution for a given switch off on duty cycle and given Q, you repeat this and you get A1 A2. So once you have A1 A2, you can, if you plot this A1 A2 versus Q, okay, versus duty cycle. So the figure which you have seen here is only for 50% duty cycle in this paper, but then once you have a code, you can see I am doing it for 3 different duty cycles. The red one is the 25%, the blue one is the 50%, and the green pair is the 75% duty cycle. Okay, here I am plotting Q versus Q1 versus Q1 Q2 versus Q at different duty cycles, right? Okay, so then I'm going to use this to plot the waveforms. So I am going to write these codes, and I want to show you a design. Okay, so I want to show you a design of a class E using this graphical technique. So let me put you on a pause. Okay, so I have written the code. I've coded those equations and sought a numerical solution of this A1 A2, and based on that I have plotted the waveform. So this is the MATLAB code doing that. So all I have to do is I have to give a certain input. So let's say I'm going to design for a resistance of 8 ohm, or let's say 10 ohm or whatever, right? So I'm going to design for a given resistance, load resistance, and then the duty cycle, let's say, is 50% over here. The Q is 6, and the frequency I'm designing for is 10 gigahertz, and the supply voltage is 3.5, and the number of harmonics I'm seeking in a solution is 19. So once I do that and hit this, okay, so oh, there is a issue here. Let me just set this right. These labels are wrong. So let me just go and correct this. Okay, so this one is X label and that one is Y label. Okay, fine. Let's run this again. Okay, so this is my ideal class E waveforms. This is the blue color is the voltage across the drain, and the green is the output voltage, and here the red is the current through the switch, and the blue one is the current through the capacitor, right? And then this green one is the output current, right? And over here we have a voltage across the device. Okay, so basically, hang on a second. So this is a voltage across the device, uh, and then this one is the output power delivered. So right now with 3.5 volt I'm delivering 29 dpm out at 10 gigahertz, and then this second harmonic is around 7, so there is a difference of, or 8, so there is a difference of 21 dB between fundamental and second harmonic, right? And all other harmonics are way lower. So looking at the result here, okay, so the CSH shunt capacitor is 4.09 or 0.409 picofarad. The series capacitor is 0.419, and series inductor is 7.6 nanohenry, right? So now this is difficult to implement on chip, so I'll play with this to get this number lower than let's say 5 nanohenry, so that I can implement it on chip. And the device utilization factor is 0.98, roughly 0.98, and then the peak voltage is 6.5 times of the supply voltage roughly, right? So that's there. So this is I peak and V peak are device stress, so which I didn't discuss here in the form of equations, but then the paper discusses the device stress here. And also the previous session, the paper by Nathan Sokal 1975 also discusses the stress, the device stress, which I haven't discussed, though I have coded over here. So once we have this, we have to validate whether our code is correct. So the way to do that is, the simplest way to do that is going to be, you implement the circuit in ADS, right? And after that, this ideal circuit, I'm going to replace the switch with the device. So once I have done that, I would have implementation. So probably in the next session I will do the implementation of class E as a mimic at a low frequency. So I might not pick up 10 gigahertz, but I might pick up something in C band. Okay, so here I'm going to try to see if these are correct. Okay, so I'm going to make a new workspace and call it ideal class E. So I'll make a new workspace. I'll call this one as ideal class E, right? And I'm not going to attach anything, so I'm not attaching any libraries, right? Say create workspace, Later I'm going to implement this in Corvo or Triquint process. Okay, so I'm going to use anything in Micron. That's okay. Finish it. Okay, so I have a blank workspace here. I'm going to make a new schematic and call this as a ideal class E NEQ. So this is for NEQ, NED, any duty cycle. Create schematic. Okay, so let me just make sure I'm recording it. Okay, fine. So what I'm going to do is create this circuit here, which is going to be C shunt as 0.4092 or 4093. So I'll go to lump components. Okay, capacitor, and I will put here as 0.4093, correct? And then I'm going to put here a series cap. Series cap is 0.4195, 0.4195, right? And then the inductance is 7.639 or 7.64. 7.64 is the inductance. Okay, 7.64 is the inductance. And then I have a load of 8 ohms, correct? So I'll put here a load of 8 ohms. That's what I designed for. Now well, it's very simple. If you want to go from 8 ohm to 50 ohm, just put a quarter wave line at your frequency of interest of a characteristic impedance which is a geometric mean of 8 and 50. So that's very simple. We will do this later on, but let's look it in an 8 ohm system. So I'm going to measure currents here. So I'm going to put here DC probe. So probe components. Okay, so I'm going to put here IO. Name this node as a VO. Name this node as VO. Okay, so that's all set. Here what I'm going to do is I'm going to put here also a probe. So same probe, I'm going to just copy this, rotate it out, put it over here, but here I am going to call this is ICSH. Okay, so this is through the shunt capacitor, current through shunt capacitor. Then I'm going to put here a ideal switch from system. Where do I find it? System, switch and algorithmic. I'm going to put here a static switch here, right? So basically it's switching between two paths, right? So I'm going to rotate this. Okay, so right now if the so I'm not going to put any of this stuff. Isolation is 100. Yeah, so where is the turn on voltage for this one? Just 1 second. Hang on a second. This is static switch, right? Static switch V, that's what I'm going to use. Voltage controlled static switch. So just swap it. That's correct. So if the voltage 1, voltage 2, okay, so I'm going to make this voltage 1 is 0.95. So the switching takes place here. Then I'm going to have a on resistance of, let's say, 0.01 or milliohm, right? And then I am going to have of resistance of let's say 20 mega. Okay, and say okay. And the model here, instance name, hang on, single pole double throw switch, switch V. Okay, that's okay. Okay, so there is no model name. Let's try this out. If it works, otherwise we'll swap it. Okay, so oh, this is a model, that's why. Where is the component for this one? This is the component. Sorry, I did a mistake here. Okay, so this is the component. Fine, so I'm not going to use any model here, so let's remove the model. And this one is going to be V1. I'm going to make it as 0.095, or rather 95, sorry, 0.95, and 1 volt. And this is going to be 20 mega ohm, and this is going to be 1 milliohm. Okay, and then I am going to have this here, and I'm going to put a probe in here to see the switch current. So I'm going to just copy this probe and ISW. Okay, so this I will name as ISW. Correct. So this is going to be your current through the switch, and then I'm going to ground this, and I can put here a sine wave if I want. I can put a square wave if I want. So let's put here sources frequency domain, and let's say I'm going to put here P1 tone. Really it doesn't matter. And let's say I'm going to do this at 10 gigahertz, because this is designed for 10 gigahertz, right? And let's put in a power of like 15 dBm or something, so enough voltage swing is there, and that I will connect over here. So basically this is just a signal to switch on and off the switch. And then I'm going to use a LUM component, and then I'm going to use a DC feed, which is equivalent to a RFC, radio frequency choke. It only lets the DC through. In a practical circuit you will implement this using a using bias decoupling, using tank circuits, right, which you do it at fundamentals and third harmonics, fundamental, second harmonic, third harmonic, and so on, right? So I will design the decoupling for 10 and 20 gigahertz to operate this in classy mode. Okay, then there is a supply voltage, sources frequency domain of 3.5 volts, 3.5 volts. Correct. And if you want to measure the drain current, you can measure the drain current over here. So I will call this as ID, as in our equations, right? So this is going to be ID. Okay, so now we are all set. Okay, okay, so now let's see, let's name this as VD. This node is VD, sorry, VD. Okay, so now we are going to plot the waveforms, right? So let's do a harmonic balance simulation on this. Simulation HB, and I am going to run this HB at 10 gigahertz. I'm going to choose 19 harmonics, right? Okay, and say okay. So I'm not going to look at output power, and I'm just going to look at the voltage waveforms first, and then we will think about the powers, Okay, so we are ready for simulation. Hang on a second. Yeah, order of this is fine. So I'm gonna hit simulate. Unless there is a big error somewhere, I'm okay. Okay, so this is a Matlab response, and now I'm going to compare this to harmonic balance here. Okay, so I'm going to plot the voltage waveform across the switch. So VD I'm going to plot add time domain signal. Okay, what has happened here? Let me see if all the numbers are correct. LS is 7.6. Oh, there's a mistake here. This is 0.7639 nanohenry. 0.7639 nanohenry. There is a mistake here. 0.7639 nanohenry. So now it's okay. One typing mistake. Okay, so this looks like class E. Not exactly. Let's put here 4. Okay, let's increase the number of harmonics to, let's say, 39 and hit simulate. Okay, so now here slope is the issue, so I am just going to tell you the numbers. This is 4.0927. 4.0927 or 93 is okay, and this is 0.4195, and this is 0.7639. So the numbers are almost okay. Okay, so what I'm going to do is, so this is, I'm going to plot the output voltage time domain. Okay, so this is my output voltage. Then I'm going to look at the currents. So I'm going to put here I switch at time domain. So this is I switch doing it, so I understand what's going on here. And then I'm going to look at ISH time domain. Okay, so here, okay, so here let's increase the harmonics. So let's say for argument's sake 101, large number. Okay, so basically why there is a this thing here. So let's see if there is something wrong here. We designed for 8 ohm, isn't it? So R, DPR, Q, frequency, VDC, NHR. Okay, so 50% duty cycle. Is it 50% duty cycle? Hang on. This guy, right? Let's put here V pulse. Okay, V pulse. Sources, frequency domain. So we have got V pulse. Or rather V square will also do, right? Okay, let's see what this is. So I am going to have a peak voltage of, let's say, 5 volts, a frequency of 10 gigahertz. So 0.05 or 49, and rise time is 0.01 fall time is 001. Correct? So that makes sense. Let's put here same harmonic 19. Let's put here 19 harmonics. Let's hit simulate now. I think what happened was the duty cycle issue. Yeah, so now this makes sense. Okay, so what was happening was the duty cycle which I was feeding here is now exactly 50%, right? So now I can increase the number harmonics to, let's say, 39, for example, an odd number. And sorry, I don't want to do a tune. So hit simulate. Okay, so this one is your waveform, which I'm also getting from Matlab, right? Okay, so it's just that it is basically starting at a different reference level, right? So that's here. Okay, so it doesn't matter. So we are getting same response here and here. You can compare this. So our code is basically accurate. You don't have to do any tweaking or anything. So the code is for classy design is accurate. Now let's look at the output power, right? So output power, I am going to, okay, I'm also going to look at VD spectrum. So I'm going to look at VD and I want to draw a spectrum magnitude maybe. Okay, so VD spectrum is this. So there is something which I added in the code which I shouldn't have. Okay, so this one is fine. So let's run this again. Okay, so now this is 6.05 and this one is for 5.7. Okay, so there is a slight difference here in terms of fundamental and harmonics of this voltage, the voltage across the switch. Let's look at the output power. So I can do a VO and say spectrum in dBm, and I'm putting out here 21. So let's look at the supply voltage here. Supply voltage is 3.5. So why am I putting out 21? Okay, this is a 8 ohm system, so this is computing in a wrong way. So the way to compute this would be, I write a equation, measurement equation. I will go to harmonic balance measurement equations, or measurement equation, because this is not a 50 ohm system, so that formula for dBm is wrong. So I can say P out is equal to 0.5 times of 0.5 times of real of V out, this is capital V out, into conjugate of I out dot I, correct? This is P out, and in dBm there will be 10 log 10 of that, so 10 times of log 10 of this plus 30, so that's correct. So now I am going to do P out. So this P out is wrong. I'm going to delete this one. I am going to plot P out. Okay, and I want to put this in plot type to be plot type, trace type. Okay, so now let's put a marker over here. Okay, so this is 29.042. This is from harmonic balance simulation, and if I go here and here, it is 29.0432. 29.0432, rather we have 2, and this one is going to be 7.73. 7.73 is 7.8 here, and from Matlab this is 7.79 or 7.8. 7.8 here, 7.8 here. So basically this design is fairly accurate compared, validated by harmonic balance. So this MATLAB code is doing a good job, right? So this MATLAB code is doing a good job compared to the harmonic balance. Just one second. Compared to the harmonic balance, let me just align them so that you can see all together. And fit. So this is your harmonic balance result for the same design, and this waveforms we are seeing these are from Matlab. Okay, so these are from Matlab. Okay, and I'm going to put here a text which says that this is harmonic balance. Harmonic balance validation. Okay, and then this is Matlab. Okay, so I have validated my code, right? And even power levels come out to be correct, right? So I'm going to stop here, and in the next session I will implement a mimic for this class E in a Corvo process. Thanks a lot. Thank you.